There's a couple robotaxi examples, but there's also pictures of cats. So this is a more traditional machine learning AI kind of talk. But the idea here is to not get deep into the mechanisms, but rather to talk about the types of capabilities you'll see. So it's a high-level understanding to make sure everyone knows the kind of different capabilities and the kind of mechanisms. Now, no doubt, everything I say, someone can nitpick and find a little thing that, well, there's a special case, and yeah, I get all that. This is a high-level overview to make sure everyone's straight on the big picture. And there's a lot more detail we could go into. If it's important, we could do in Q&A, but we're going to keep it high level to make sure everyone gets the big picture, because there's some really high-level points and trade-offs that people lose track of in the enthusiasm for this technology. So I'm going to talk about machine learning-based AI, useful capabilities. So I'm going to categorize them as classification, end-to-end, generative AI, large language models. I know there's a lot of detail beyond that, but those are the 4 bins that sort of get the point across for our purposes. I'm going to talk about some of the challenges to using ML, machine learning, biases, hallucinations, and you'll notice there's quotes around those because these things are not people. That's us projecting human attributes on the technology that doesn't actually have what's implied by those attributes. And there's some practical issues like edge cases, accountability to autonowashing. Very briefly, I talk about AI safety. And this is all my take on trying to give some high-level ideas so that we can reason effectively about where machine learning makes sense, where it doesn't, the strengths, the pitfalls, and so on. Fundamentally, machine learning is learning by example. Traditional software, it's algorithm-based. If you know how to write an algorithm, you should probably do that and write the algorithm, because then you don't have to deal with all the pitfalls. Yeah, doing machine learning may be quicker, but you're going to have to deal with a lot of pitfalls. So traditional software is not going away. Why do we need machine learning then? Well, machine learning does amazing, impressive stuff, and it works by a statistical approach. So rather than a person having to say step 1, step 2, step 3, we all had that algorithms class. If you took a programming class, somebody started with a flow chart or step 1, step 2, right? Machine learning does not work that way. It's a statistical approach. And fundamentally it says, hey, I want to know what a cat looks like. And trying to write down a step-by-step approach for what a cat looks like is really, really tough. AI researchers struggled for decades with this kind of problem. And machine learning says, I don't care about the steps. Hey, let me show you a bazillion cats. Statistical machine, figure it out. And the statistical machinery, it's called learning. It's not quite like a person learns, but it's called learning. It adjusts and fiddles and fiddles and fiddles and gradient ascents some statistics until it has a good statistical approximation of picture comes in, label a determination of whether it's a cat or not comes out. Requires tons and tons of data. In this case, label data. Here's a picture, here's a cat, here's a picture, here's a cat. And eventually it figures out by statistics what it means to be catness. So you're training a statistical model fit. It's curve fitting, very, very multidimensional. It's nonlinear, but fundamentally it's curve fitting to catness. Okay, great. Now, what can we do with that? Well, the first capability I will talk about is classification. So a class is what type of object is being detected. So that's what we mean by class. And an ML model is the bunch of statistics that got trained on what it means to have catness. Each example in the training has a cat, and it may be just cat or person if it's a binary classifier, cat or person, and you repeat the training to improve the classification over time. You train and say, well, you could do better here, and so let's try it again. Eventually, the model is supposed to converge to something that's really good at telling a cat from a person. So in practice, for classification, you just say, here's a picture, and you have to have something of saying, oh, by the way, here's an object. Details for our discussion. But we'll draw a box, and you say, well, is it a cat or is it a person? And you only notice 2 things, cat or person. They say, oh, okay, that one's a person, because most of that picture looks like a person. And then, oh, there's also a cat, because that box looks kind of like a cat. But there's an important, really deep thing to keep in mind. It is not saying it's a cat. It does not know what a cat is the way a person would understand the concept of cat. What it's saying is that thing, that set of pixels, looks awfully similar to all the things that someone told me were cats. So it looks like the cats I trained on, which is not the same as knowing what a cat is. There are deep arguments that folks may disagree with this, but I'm going to take a high-level approach. There's a difference between a cat, a picture of a cat, and a thing that looks statistically like a cat. And this is saying this looks like the cats I trained on. Well, why does that matter? Well, the reason that distinction matters is because we get issues of bias. Now, bias is a human attribute. These machines are not human. We call it bias because that people understand what bias means. But there's some implications which may or may not be true, but it isn't bias, it's faulty training data. Now, how can the training data be faulty? Well, one thing is it may have missing data. What if there's not a single calico cat in the training database? When it sees a calico cat, it'll go, I have no idea, right? And it may just randomly guess. So if it hasn't seen something, it's hard for it to deduce from first principles, oh, that's a cat, because it looks like all the other cats except different fur color. And we see issues. There was recently in the news a thing about fire engines weren't spotted because they weren't painted red. This is actually a thing. Color actually matters for these kind of things. You may get overrepresented classes of data. What if we trained only on black cats? If it sees any cat color other than black, it may have no idea it's a cat. Or maybe we train on 1 million black cats and 1 white cat. And it says, all right, you know what? I can ignore the white cat because I'm still right 99 times out of 1 million. Oh, never mind. We don't care about white cats. Close enough because it's statistics. So you get bias, which was what we call it, when you underrepresent some classes of data or overrepresent others, and it comes to conclusions that don't correspond to the same conclusions a person would, because it just statistically hasn't been trained properly. There are also the risk of chance statistical correlations. So what if, now I did an image search for children classes to be sure, so I'm not saying the tool did this on purpose, but what if it turns out every single child you trained on has glasses? There's a risk the machine learning, pretty good one, will learn that, well, I don't care about children, I'm just looking for glasses here. And if it finds a glass, if it's glasses, it's probably a child, that's good. Statistically, that works just fine. So there's a real issue with making sure you don't have chance statistical correlations, which is a different aspect of the overrepresentation, underrepresentation. So you can get problematic machine learning outcomes, such as poor accuracy at underrepresented data, or the other one is false confidence. These things love to be super confident when they're just guessing. And the training mechanism, unless you do something special, the training mechanism basically is prone to doing that. When you're done doing all the curve fitting, it's either really sure it's a yes or a no, and if it's something it hasn't seen before, it'll just force it into a bin. So if you're doing an application, you have to keep this in mind. What about another capability, end-to-end behavior? So what's the right response to a stimulus? The problem, one of the problems with classification in supervised learning, as it's called, is that you have to pay people in self-driving car business, thousands of people, to label images saying, yep, that's car, that's pedestrian, that's a tree, whatever. Multiple companies have 1,000 or more people doing this. And that gets expensive and it's error prone. There's another thing you can do is say, oh, forget that. We're not going to label it all. We're just going to show it a picture and have it react based on what it sees, right? So that's our plan. We're going to train the ML model on its behavior. Each situation has a reward for acceptable behavior. It's called reinforcement learning, and we're going to do repeated training to maximize the reward score. So what do we have here? Here's a picture you may see. Let's say there's a camera in the car and it sees, turns out there's 2 bicyclists if you look closely. And what it does, it runs through a simulator a bunch of times, and sometimes it turns right and hits the bicyclist and you say that's bad. And sometimes it goes straight and maybe nearly misses them, and that's not so good. And then sometimes it swerves left and that's good. And you just run the simulations over and over and over. You give it a score of how it's doing, and it hill climbs the score until it gets a good score by modifying its behavior. So the thing here is you may not have a human interpretable classification. There may be nothing in the machine learning that knows what a pedestrian is. Maybe it invents 2 people bikes that happen to be close. Who knows what it invents? But what you do know is statistically, when it sees something that looks like a bicyclist, it's going to swerve left and you're going to go, okay, that's fine. It's learned how to drive. So the important thing here is we don't actually know what it's learning or why it's learning. We just know the outcome is something we like. Now, there's a challenge here, which is validation. And the point of validation is pretty subtle. Traditionally, lots of us have seen the V model. Down the left-hand side is the design, up the right-hand side is the test. But there's a critical part of the V model for life-critical, safety-critical systems that's subtle but super important. The reason testing works on the right is not because we test everything. It's because we test things that correspond to the left. That's the traceability and validation horizontal lines. But the reason we're able to do limited testing instead of testing everything is because we have a causal path through the V that here's our requirements, and we're pretty sure the thing does the requirements because we did design, because we did implementation, and we did verification up and down to make sure each step matches the next. So by the time you get to acceptance test, you don't have to test everything because you're pretty sure it's solid, and you're just making sure somebody didn't make a mistake missing the requirements. So the testing is a quality exercise on the design process rather than testing to make sure everything possible wrong isn't there, because you already know it's probably right because you did the design process. But you stick machine learning in at the bottom levels, and you break the causal connection between the left side of the V and the right side of the V. The machine learning just learns some behavior, and who knows what happened? Who knows whether it's implementing the requirements on purpose or just by chance? Now there are lots of techniques you can apply here, but in the naive application of machine learning, you just get a result and you have no idea why it works. You have actually no idea what it does until you try it out. And so you still can have traceability. You can say, well, I have an acceptance test and it tests the product requirements. But the background expectation that the product requirements are connected to the behavior because of the rigorous engineering process is broken because machine learning just does what it does. This is a huge challenge. Lots of people are working on trying to get the V mapped to machine learning, but it's very easy to miss the fact that the V works because of a causal, it's a Bayesian prior expectation, a causal connection between the tests and the design, and machine learning breaks that unless you have another story to tell. So you have validation challenges, the data set sufficiency and balance. Did the ML exploit chance data correlations? Are there biases we didn't think to check? Are there discontinuities in behavior? How brittle is the system to surprises? And to be sure, for example, in the self-driving area, there are standards out that deal with all these things. But you have to realize that naively doing the V with machine learning doesn't work because the V is based on an assumption that there's verification up and down both sides, and machine learning breaks that. The next capability is generative outputs. You can create a synthetic print picture, and we've all seen synthetic pictures. In fact, this talk is full of them as illustrations. I've labeled them all AI generated for transparency. The machine learning model outputs complex data from a comparatively simple prompt. And so I may say, give me a city street with a car passing a bicyclist, and I get some candidates, and I say, sure, I'll show that picture in my talk. Okay, great. It's really amazing that it can do this. I mean, just astonishing. Even a few years ago, it wasn't even close. This is just astonishing technology. But the thing you have to keep in mind is this is not a city street with a car passing a bicyclist. It's a thing statistically similar to a car, and a thing statistically similar to a bicyclist, and a situation statistically similar to passing, and a situation statistically similar to city street. So somehow it had to figure out what all those concepts mean by mapping it in, and probably using a large language model to parse the prompt. We'll get to those in a minute. And it's amazing that these outputs can be so good. And you can imagine using this, for example, it's expensive to collect training data and it's expensive to build simulations. So why don't we just do a lot of generative AI to show images to train our self-driving car, or to show images to do whatever we want? It's cheaper than hiring a camera person to go out and take pictures. So you might use this for synthetic training data. And so there's a lot of promise there, and companies are definitely going down this path. But what's a challenge? The big challenge is edge cases. So an edge case is an object or situation not learned from training data. There's various definitions, but that's one we're going to use for now. It's an object or situation that you didn't learn from the training data. It might not be in the training data at all, or it might be in the training data and it's so rare you didn't notice it, or it was so rare that it didn't affect the statistics enough, or maybe the system got lucky on that particular training data, but would have gotten it wrong on something else. So it's stuff that's just hidden in the noise. The problem, especially with safety critical systems, is safety is dominated by low probability, high consequence events. And so edge cases are a thing. We're going to come back to that. So what does this mean in practice? Well, if you have some cats, you can say, show me a bunch of pictures of cats. And the world can be heavy tail. So there's the long tail, which is the rare events, but heavy tail is a proposition that the rare events are rare individually, but there's so many of them, you cannot afford to ignore them. And there's plenty of signs the real world works this way for machine learning applications. There are huge numbers of edge cases. They might be 1 in a million, but if there's 10 million, 1 in a million cases, well, they're showing up all the time, right? By the way, is that really a cat? Google image search thought it was, but I'm going to say it looks like an actor dressed up as a cat. Those are the kind of things you have to watch out for. So machine learning is especially bad at knowing that it's clueless. If it's not sure, it'll guess. If it's just, well, those pixels on that person dressed up as a cat, that's pretty cat-like, so I'm going with cat. And maybe it doesn't have a bin for person dressed up as a cat. It said, well, more cat than person, so yeah, we're going with cat. What if the training has incorrect or missing high criticality situations? What if the training data used automatic labeling and told the machine learning, indeed, that's a cat? Now it's going to learn that people dressed up like cats are cats, and that can be a problem if there's one out on the road and you're deciding what to do in a risky crash-like situation. Ultimately, the limit to machine learning safety is edge cases. That's just a fundamental thing, that it's a statistical technology. We're going to get back to safety, but ultimately the limit is edge cases, in particular on classification and prediction. Next capability, foundation models. Tell me a story. Create a plausible string of outputs. And lots of people are having lots of fun with this, and it is an amazing technology. I asked Microsoft Copilot, hey, I want a story about a city street with a car passing a bicycle. And I got this long narrative, which you read it, it's okay. It's grammatically okay, and it tells a story, and it talks about Sarah, and it talks about Mark, and so on. Well, how do you get this? You train on a huge corpus of data, like all the books ever printed, or the entire internet, or both, and you look for which symbols tend to be used near which other, and which words tend to be used in similar sequences. So this is not building an explicit model of the world. That's not what's happening. What's happening is it's just saying, well, if you show me some words, I think I can guess what happens next. Some people call it autocomplete on steroids. It's the autocomplete technology. It can be a little more sophisticated. It can do some things in parallel, but basically it amounts to, given some preceding text, which starts with huge amounts of text, and then you ask it a question and it says, well, let me continue what you said and go on. You can do amazing things with this. There are lots of issues with, which I'll get to, but you can do amazing stuff with this. It's super impressive technology. And something important is every time you ask it, you get a different answer. So the first time it gave me Sarah and Mark, and the second time it gave me Alex and Mia, and it was a different story. And that's great, because now you can think of, for example, asking a large language model, a foundation model, to say, all right, show me a city street with a bicyclist and a car passing it, give me a description of a story, and then feed that story into a generative AI system to produce a picture or a video. You can do some really powerful stuff with this if you want to train robotaxi, but there's lots of other stuff for good and bad. We're seeing applications of this all over the place. Okay, there's a challenge. People call it hallucinations. I'm just going to call it bullshit as a technical term. It is actually a technical term. Bullshit means superficially plausible, but with an utter lack of concern about the truth. So saying it's lying is wrong. Saying it's telling the truth is wrong. It is bullshitting, which means it's saying what it's saying, and the concept of truth and lie are just not concepts it's concerned with. It's going to say what it's going to say. I really don't like hallucinations because it implies that things that are incorrect are somehow hallucinations, and that's not what's going on. If you want to use the word hallucination, everything these produce is a hallucination, and the truth is projected on it by the reader, right? It doesn't know hallucination. Now, there's some really cool stuff. 10 people showing their hands, I asked DALL-E 3, and it gave me this picture. And if you glance at it, it's like, hey, there's a bunch of hands. Then you look a little closer. Is that guy's name Joe Hand? I don't know what he's doing there. Maybe his last name is Hand. I don't know. But then you start counting fingers. And, well, statistically, there's about the right number of fingers on average, but some of the pictures are a little disturbing. And this one indeed has 4 fingers, but you got a little problem with the thumbs there, okay? And it's pretty common. There's a great sport of the political generated images that are going to go around for the political campaign. There's a great sport of trying to find the flaws and usually look for people's hands. That's always the tell. And eventually the technology will improve and people will figure out how to get these things to always put the right number of fingers on hands. And, that's great. So it isn't about the hands. It's about when you glance at the picture, you don't notice anything wrong. But then when you go into details, you start noticing some problems. It's a statistically plausible picture, which is different than the truth, right? Truth is not a factor in any machine learning output. It doesn't know what true is. These days, people struggle with deciding what's truth, what's fiction, but the machine learning doesn't do that. Statistical accuracy is not the truth. Now, there's a technique where you take machine learning and you couple it to something real world that is thought to be the truth and say, well, I'm just summarizing this real thing, so it must be true. And so I had a little fun. This one I came up with, I said, hey, can a mouse get trapped in your ear? And the answer is yes, a mouse can get trapped in your ear. In fact, if you read this guest blog, so it points to a single article, just one article. And if you read the guest blog, it's about someone writing creative fiction about how a mouse has set up a living room inside her ear because it feels that way. It's not literally true. And she sarcastically says she went to the doctor and he said, take a lot of Mucinex and things like this. But it was all any human reader would say she was just telling a story. But the AI didn't know that. The AI said, yeah, you sure enough, you're getting a mouse trapped in your ear. Because its idea of truth for this is, I found it on the web. And we all know, this is sarcasm, just to be clear, we all know how absolutely everything on the web is 100% true. End of sarcasm, all right? So, and again, this will improve over time. But you have to realize that these things at their heart are just making up statistical stuff. Right, they're bullshitting. And there are things you can put on to improve the quality and some safety guardrails you can put on, but you have to understand that's the core of the technology. So it's always going to be a struggle. The next challenge is autonowashing. So autonowashing is greenwashing of vehicle automation, thanks to Liza Dixon for coining that cool term. And here's an example. This is the infamous Tesla Paint It Black commercial where they said the person in the driver's seat is there only for legal reasons. He's not doing anything. The car is driving itself. And it has since come out that there were many, many takes. There was a car crash and basically it was all just fantasy. And they just happened to catch this car driving for a little bit at a time and pasted them together. All right. So people to this day believe that kind of video or the cool, hey, this time it did this cool thing are representative of typical performance. And that's not really the truth. It hasn't been for a long while. And there's some robotaxis going around that do a lot better. But the issue is public perception is affected by fantasy videos. And there's a problem that machine learning used for AI can create fantasies that people believe more than they should. This applies generally to AI hype. There's all sorts of things being said about AI that just aren't true. They're just wishful thinking, but you get a couple cool demos and people get sucked in and they start believing. Now, can I make this concrete? Sure. There are unrealistic claims already leading to harm. One is brand tarnish via eroded quality. And there's pointers in here. I'm happy to make these slides available. I'll put them up on social media. You can check these out. But one story was someone asked a chatbot about the bereavement fares for an airline. They said, don't worry about it. Send it in later. We'll deal with it. And then the airline rejected it, saying, no, you have to do it in advance. And the person said, your chatbot promised me it was okay. And they said, oh, you can't trust a chatbot. That doesn't count. And the airline lost the lawsuit, right? But that was brand tarnish because I've heard about that. Lots of people heard about that. There's going to be brand tarnish by having unreliable chatbot and other services dealing with customers. So yeah, you can reduce customer costs, but don't forget, you risk brand tarnish if you're not careful. There's also undue trust for use in critical tasks. We've seen drunk drivers over-trusting self-driving features from more than one company, ending up in at least some fatalities here. And what's going on? Well, they've been told the car is a better driver than they are. And they say, well, I'm drunk. The car drives better than me. I'll let it drive me. And the messaging didn't make it clear that it's only a better driver because we're counting on the person to save it when it makes a mistake. That gets past them. They don't hear it, or they're drunk, and the nuances don't really register at the time. But we've seen people hurt and killed because of unjustified confidence in AI performance. And there's automation complacency, degraded fact-checking. There's a lawyer who was sanctioned and had to write apology letters to judges because he filed a legal brief generated by ChatGPT or a competitor that was full of completely made-up citations, all right? People say, we just need education. Education never fixed anything like this. It makes it better, but if you hype and spin and advertise and tell people this stuff does things it can't do, education isn't going to fix it. It's a much worse problem than that, because people want to believe in the magic. They want to believe, and education is a comparatively ineffective tool at combating that. Okay, how about artificial general intelligence? AGI. Some people say we're about to get artificial general intelligence. I'm going to use a simple definition of it matches human capabilities in more than one task. So it's not just it can drive. It's not just it can summarize articles and tell you what the summary is. It can do many things that humans can do. And people are worried this is going to be here any day. Some people are saying that machine learning systems have AGI, or large language models are basically AGI, just they're not done with it yet. I don't buy any of that stuff. Well, let me go through some of it. There's the Turing test. Oh, if you can pass the Turing test, that means you're an AI. That was never really true. If you look up, it was sort of, if you can pass a Turing test, then if you can't pass a Turing test, you're not an AI. What's a Turing test? There's somebody on the other end of a typewritten, of a direct messaging system or a chat system, and you cannot tell whether they're a computer or a person. That's the Turing test. Well, chatbots have gotten really good. And it turned out decades ago, some people were sucked in by very primitive chatbots. One of them, a famous one, is called Eliza. Some people would be sucked in for a while. And now more people are sucked in. And it turns out the Turing test, once the technology advances to the point that some people are fooled, turns out to be more a test of human gullibility than general AI. So if you can't pass a Turing test, there's nothing to talk about. But passing it just proves you're good at faking how to be a human, which is a little different. You see machine learning systems passing college exams and IQ tests. More than likely, the training corpus included all the stuff in those tests one way or another. So yeah, I mean, it's really cool that it's a query system. It's like going on the web and finding the answers, except easier. And maybe it's a little more creative, but it doesn't prove it's smart. It proves it can pass an IQ test to the degree that IQ tests ever proved people were smart. There's a whole controversy there. Machine learning-based systems do not understand. That's what's important. They don't understand. They train on the results of understanding, not the same as understanding. The map is not the territory. Memorizing a map is not the same as an ability to go out, look at a territory, and draw a map. Looking at a bunch of territories and looking at a bunch of maps and saying, well, I bet the map for this territory is the same as all those others, is a nice shortcut, but it's not the same as actually understanding the territory. And brittleness to novelty is a huge issue. Those kind of techniques work great unless something's different, and the machine learning may not even understand that it's different and just sort of fake an answer that misses something really important. So when I use machine learning to try and summarize things for me, what I find is the parts that I found the most interesting as a researcher are often missing from the summary, because the summary is about what most of the words say and not the ideas. Okay, we need additional breakthroughs for AGI. Or just take a look at how these things behave. Stupid is as stupid does. Okay, another challenge is AI safety and accountability. System safety is about edge cases, near zero probability time, and catastrophic consequences. Lots of systems are unforgiving of small errors. Statistics has trouble with a bunch of nines, and I'll leave it there. I've given lots of other talks about that. But I'm not worried about Skynet. I'm just not. That's not what I'm worried about. I'm worried about three themes for AI safety. The first is, if you build an AI, and when I say AI, machine learning, but I'll use AI for short. When you build an AI system and trust it to do things, Basically, who's accountable for harm? One way for a company to avoid being blamed for harm is to blame the computer as if it wasn't their fault. And this is actually state law in some states for self-driving cars. So this is a thing. If you build a computer, you can avoid accountability for harm. That's a problem. That's not the AIs taking over the world. That's people misusing the technology. There's transparency equity issues. You can blame an opaque computer for evading accountability. If a computer has what a person would call biased behavior, that it discriminates against certain classes of people or puts some people at risk, you can say, well, it's the computer's fault. I have no idea how it was built. And it's another way of shirking accountability. And the last one is it's a terrible tool for disinformation and malicious use. We're going to see so much of this for bad, reckless, and power-hungry. So I don't worry about Skynet. I worry about these three misuses of the technology, which all trace back to people generally intentionally using the technology for bad purposes, sometimes doing it because they're clueless. That's what I worry about for AI safety. So what about ML and the 90-10 principle? So this is my last substantive slide here, and then we have a wrap up. 90-10 principle, 90% of the benefit from the first 10%. They're going, well, statistical, if we can get 90% of the benefit, shouldn't we do it? Well, sometimes, but let's talk about that. The pros for machine learning is it's great for quick prototyping. It's great for creating fictional material. It's great for creating eye candy for slides like I've been doing in this presentation. And sometimes good enough is good enough. And if good enough is good enough, that's fantastic. But you need to be aware of the limitations and make sure those limitations do not have high consequence for your application. It lacks common sense. And again, that's in quotes because that's a personal term that there is no common sense. It's just statistics. But that manifests as, hey, I hit something that I'm not sure what's going on. I'm just going to take a guess. Whereas a person would say, that doesn't sound right. I think I'm going to think a little bit harder about this before I just guess. The effort to check the outputs may outweigh the advantages. So if you have a model writing drafts, sometimes fixing a draft is more expensive than writing one from scratch. It depends. There's a sweet spot there, but you have to pay attention to make sure you're not doing more work to clean up the mess. For sure, there's a sweet spot. That's a risk that can be a real problem. Intellectual property issues with training data, that's all in the news. Are you paying people you're training on? Is that going to come back to bite you? In particular, if you generate an automatic picture and it turns out to be really similar to someone else's, you might find yourself getting sued, and those kind of things are already happening, especially with very distinctive style artwork. 90% correct doesn't mean 90% functional, so smells right may or may not be good enough for your application. And the last one is the disinformation risk. You've all been looking at this glass of water 90% full. It's not. It's about 75 or 80% full. And if enough people look at a picture that's 90% full, I measured it with a ruler on my screen just to be sure, because it didn't look right to me. But if enough people see that picture enough times, they're actually going to grow up not knowing what 90% is. So some very, very subtle corrosive possibilities for this technology. So wrapping up, machine learning-based AI is not self-aware. Okay, it's the statistical transformation of input to output. If there's any truth, it's what you project onto the AI. It's not about truth, it's about statistics, and those are not quite the same. The strengths are it has good performance on the common case, it has superficially reasonable outputs, and that can be very useful, very powerful if you understand its limitations. The weaknesses are that people tend to overtrust not necessarily reliable outputs. You get automation complacency, and it generates bullshit, again, using that as a technical term. And, the devil's in the details. Take another look at that picture.